welcome, Professor Anantram, okay,
Hi,
to one more interview for the IEEE NANO2024. To start this interview, could you start by telling us a little bit about your own research career in your own words?
Okay, yeah. So, I have a master's in physics, specializing in condensed matter physics, and a bachelor's in applied science. And, I came to kind of do my PhD in physics at Purdue University, and kind of started working with a Polish physicist who moved back to Poland. So, and so I needed a PhD supervisor, and that's when I kind of, with advice from some good faculty members at the Purdue Physics Department, I became a student of Supriya Datta, who was in the electrical engineering department. But that also required me to pivot and move from the physics department to the electrical engineering department. And so that's how I kind of got involved in this field of transport and nanoscale materials and devices. So kind of after that, I did a brief postdoc in a slightly different field, which was in physics of computing. And it was good. I actually worked a little bit on cellular automata-based methods for computing, looking at the stability of the systems, and also briefly on quantum computing. But I didn't kind of stay on it for a long time. And I did look for faculty positions at that time, but was not successful in even getting an interview. So I had to decide whether I'd move to industry. And then there's this opening that came up at NASA Ames Research Center. And I applied to that, and I got the job. So I was at this point where I decided whether I want to move to NASA and become more of a computational engineer or computational scientist, because until then I'd done mainly more theory-oriented work, or if I want to move to the industry. So I kind of moved to NASA, where I had a couple of great mentors, and one of the mentors basically took me into the world of computational modeling. So until my postdoc, I had not worked on computational modeling per se. It was mainly pen and paper type theory, and a little bit of computer programming, I'd say, but mainly using someone else's code during my postdoc. And so I actually had to learn how to code properly and understand things from more of a mathematical algorithm, viewpoint in my first job. And luckily I had someone who kind of, a kind of really good computational engineer, by name T.R. Govindan, who kind of, educated me on these things. And so I stayed at NASA for about a little more than 9 years at the NASA Ames Research Center, looking at various aspects of modeling materials and devices. And then I moved to the University of Waterloo for 2.5 years, and then been at now University of Washington for a number of years, in the electrical and computer engineering department.
So in this transition, in this moving from the world from physics to electrical engineering, what role has the IEEE plays in your career in this transition?
Yeah, I would say that I was not very active in IEEE related activities, until a lot later in my life, when I kind of came to I think when I probably sometime during my job at NASA, and it all kind of started off with mentors saying that, hey, maybe you should volunteer to be on some technical committees for conferences. And so it kind of started off, I'd say, in a gradual manner, rather than so I'd say, as far as IEEE goes, I've been influenced by many great professors and working professionals from industry who are all IEEE members. So I would say, like, in the early part of my career, IEEE kind of gives us more of like is one of the vehicles to keep the community together, right? So there are various ways by which you kind of keep the community together. One is scientific interactions, right? That's often the most intense for any researcher and for industry professional. It's again their own research and development. So that's the strongest binding force for us. Then we look at kind of slightly allied fields, where we understand things, problems that we want to get into. And so that gives us a bigger kind of vessel by which we interact and hold things. And now, if we want to go beyond like things that we immediately understand beyond our own community, so that's, I think, where IEEE kind of played a big role for me. I've always enjoyed reading the IEEE spectrum, So this is because you learn about robotics in the IEEE spectrum. You learn about, I'm myself a theory and modeling guy, and I'll admit I know very little about fabrication, but there are a lot of articles that come on the big picture of fabrication. So again, so I'd say like some of the things like IEEE spectrum, IEEE electron device letters, where there are lots of fantastic articles on nanoscale fabrication. I've kind of enjoyed reading those and used some of the figures and information from my, in my own research. And then I'm gladly IEEE Nanotechnology Council is also moving in that direction, where there's IEEE Nanotechnology magazine, etc. Though it's not yet at the same level as electron device letters, I'm sorry, it was not the electron device letters. It's Electron Device Society's newsletter. That's what is most important, because there the articles are less technical and meant for a more general kind of audience. And the IEEE Nanotechnology Council, through its magazine, is trying to do similar things. So I feel like, so I kind of got involved, I'd say gradually, maybe over 2 or 3 decades, more and more into this. And in the IEEE Nanotechnology Council, I was the associate chair or vice chair for the TC10, for the modeling and simulation thing. And Jean-Pierre Leberton was the chair. And honestly, I was a horrible vice chair because I did nothing. Someone asked me to be the vice chair, and I didn't know how to wriggle out of it. So, so I'm giving you a tough job. You'll have to find a way to write all this. And then at some point of time, Jean-Pierre said that, hey, I'm not going to be the chair anymore. Why don't you take over? And I kind of told him that, hey, it's I'm kind of really not interested. And he said, a technical committee has to do better, so someone has to take over. So it'll be great. You're the vice chair, so why don't you take over? So he kind of guilted me into kind of, taking it. And I'd say that's when my involvement got a little bit deeper, which was, I think 4 years back or so, because I said, I kind of needed to decide like what to do with this, how to make this and really us do things together. So one of the things that I did was I got in some new people into the committee. And kind of the way I got in new people into the committee is not just via email. Sometimes I'd ask them to write how they'd contribute to the committee. Okay. Or sometimes I would, basically have a Zoom conversation with them, tell them that I want to see if you're a good fit, and then to understand like, how can I get people who were not as lazy as me? So that was my that was my kind of motivation. And so in that process, like there were few names, and I also advertised in the IEEE Nanotechnology magazine, etc. And I got a huge number of responses saying that I kind of want to be a member in the technical council, etc. So I'd kind of respond to all of them saying, "Oh, that's great. Can you write me a page on how you would contribute?" And a large number of people would not respond. So that was to me kind of a great filtering thing. But kind of three people, I think two were with Zoom and one was with kind of writing, who kind of stood out. One was, of course, our current chair, Rosa.
Mm.
Then there's Joseph in Austria, and there's Sagarika at IBM. So these were three people who were during conversations with them, and I think Sagarika might have been written followed by a conversation. I can't remember. I mean, it turned out that these people were serious about it. They were passionate about it, and they also seemed to have a kind of a better vision than I had on what can be done. So I said, okay, these are the people I need.
Amazing.
and so I would say that's when thing, and then Joseph and Rosa and Sagarika were really excellent. Like when I was the chair, they'd always be part of the meetings, give ideas and do things like that. So Joseph and Rosa and I, we organized sessions in the IEEE Nano in Spain 2 years back. Okay. Then John Pierre and I, we edited one of the IEEE Nanotechnology magazine issues. But I would say that when I talk about it, it would seem as if it's not much of work, but it does occupy some of your bandwidth. So this is kind of really for people who want to kind of contribute, because it does occupy everything. Just eats into your working time in a day, right? Just as when you look at this 10 years later, you might feel that, hey, I did 5 interviews. It might not seem like a big thing, but right now it basically eats into your research time quite a bit, slowly. So I did this, I think, for like 1.5 or 2 years. And what I felt was that both Joseph and Rosa were very kind of energetic. And in between, I also had this another MENED intern, Noor from Australia.
Mm-hmm.
She was also very energetic and pushed me to do things. So it was awesome having these 4 people, because I'd send them an email and they'd actually respond, and then it got this working relationship going. So I think after about 1.5 years or so, I said that, maybe I kind of don't, and like as a chair, you have to organize these kind of, by then she had volunteered passionate in kind of doing these things. And I feel like we have a committee right now, because I also got Emre Oren from Turkey, because I've also tried to get this a little bit wider geographical distribution in the committee members. So I've been trying to get a member from China for a long time, including now, but it's been difficult to get. I have got applicants from China, but I also have been a little bit picky and choosy, and I wanted to kind of be relevant to this. Sometimes you have someone in completely different field wanting to volunteer, and then I kind of don't see, though the person might be a good volunteer, it would be nice if they're also like someone interested in the nano and micro world, also with a component of, some component of modeling and simulation. So Emre from Turkey was doing bio-nano modeling. So, and he also works on charge transport. So I got him, and that led to this a seminar series in Turkey at Taub University, and kind of few things. So I think so. That's kind of my. So I'd say like mine was not a textbook kind of playing a role in IEEE. It kind of really got gradually built over a long time, where it really started out with looking at IEEE newsletters, electron device letter newsletters, IEEE Spectrum, then some mentors saying spend some time, and John Pierre pushing me to become the chair, and kind of now finally I feel more invested, and I really want this IEEE TC10 committee to do better and better and better. So part of my reason for staying in the committee is I just want to make sure we keep getting energetic and young people into the committee will actually move it in new directions. And, so I consider myself to be like an assistant to whoever's the chair and vice chair, and telling them we need to get good people. And so that's my long-winded answer. Yeah.
That's fantastic. And pulling a couple of those threads here, you mentioned how much having these mentorship relationships have pushed you forward, have made such a positive impact in your career. What kind of advice would you give to young professionals looking to have mentorship relationships?
So I'd say like I mean just kind of given my own personality, most of my kind of mentorships occurred in the sense that I kind of didn't go seeking for a mentor, but I would say like it was a number of things were like technical mentorship. So that's a very natural thing, technical mentorship, because I'm trying to get into nanoscale transport. So people like Supriya Datta and Mark Lundstrom, were mentors because they just know so much more about it, and you learn from interaction. When I moved to NASA, T.R. Govindan was a mentor because he kind of knew so much more about it, than me about computation, and he was willing to kind of mentor me and teach me tricks of the trade. So I'd say that a lot of my mentorships were actually more technical in nature. So I would say that in terms of maybe the John Pierre kind of getting me to be the chair of the TC10 a few years back, that was one of the non-technical things. So I'd say that start with maybe I'm not a very good example looking at it as someone who was seeking mentorship, because that's not kind of the route that I took, and I'm just looking back. I wish I had taken that route, but we all have different personalities, and there's only kind of so much you can change yourself. So I'd say there are two things to this. Okay, so one is like young people should kind of seek out and with kind of more senior people in the community, and first try to see how they can contribute to, in the case of IEEE Nanotechnology Council, they can see how to contribute to the bigger picture. And so when they try to see how to contribute to the bigger picture, it's good for them to have thought about how they can contribute, rather than just saying, I want to contribute. I mean, that I feel is a very low bar. You want to have some ideas, because this mentorship is a two-way thing. Just as a mentor stimulates the mentee's brain, the mentee also stimulates the mentor's brain, right? And we are all doing this outside of our own research and teaching and things like that, mentor. So from that viewpoint, I've had kind of excellent mentees, because they all stimulated my brain probably more than I stimulated, their brain. So it's for me, it's been a fun thing. But it's like I would say, like, try to take take half a page and find reasons, write down reasons on why you want a mentor. You know, I'd say that would make it very clear on why you want a mentor. And then one great way for younger people to find mentors is, you know, write to the IEEE Nanotechnology Council. If it's TC10, write to the TC10 chair. And we'd be able to find you mentors either within the TC10 council, or we could look for people. For example, I'd look for someone at the University of Washington. So I'd say that most of the relationships are would be like with a mentee contacting a mentor. But I'd also say it's also a good idea for a mentor to contact a potential mentee, and you don't tell them that, hey, I want to mentor you, but you tell them, hey, why don't you get involved in this? This could be a fun thing. And I feel like I feel like mentors also have a responsibility, and I mainly benefited from that because Jean-Pierre and, you know, my my management at NASA, etc., they took this interest in basically suggesting things for me to do. They probably had a need for it from a bigger perspective, but I'd say it's a two-way street. Mentors actually need to actively look for people whom they're willing to be, because sometimes mentees don't have the big picture. They are too shy. They feel awkward contacting people. Some of them might feel that they don't need a mentor. There are all these things. But the minute an older or a more senior person contacts you, you start thinking, maybe I should interact more with this person, right? So yeah, so I'd say that one thing maybe just we could also think about in a future IEEE meeting is, you know, can we do a mentorship program that goes beyond the IEEE MENED program, right? IEEE MENED is a very thing, but in terms of the IEEE Nanotechnology Council members, can we think of a more formal structure to have a big cohort of mentees in the simulation area with whom we might talk only once in 2 or 3 months, but find out what's happening in their life. Maybe they're looking for a job. Maybe they're looking for something. So yeah, so those are some of the thoughts.
Thank you very much for sharing. So to start to slowly go to the end of this interview, I'd still like to ask maybe a couple of more technical questions are going on to your research direction, what you'll be presenting at IEEE NANO 2024. So how did the idea of starting to work with DNA-based nanoengineering, how did that come up in your life?
Okay. So this happened actually in the year somewhere around 2000, where my wife has a PhD in biotechnology and knows quite a bit about DNA. And I had a colleague in my division at NASA. His name is Chris Hensey, and Chris was worked on computer visualization. So I was talking to my wife about kind of different biological molecules, trying to learn some DNA casually, and we needed stuff to, always like discussing science. And so I said that, this looks like a cool thing where you can build different, sequences. And then I've kind of chatted with my colleague, Chris Hensey at NASA. And I mentioned it casually, and he said, "You know what? Turned out that he had degrees in biology, though he was working in computer visualization. He had degrees in biology, and the U.S. has a lot of crazy people like this. You know, they studied something and doing something completely different. And so I kind of started chatting with him a little bit more about it, and then I wrote a tiny internal proposal at NASA saying that I would like to kind of calculate the electronic properties and transport properties of different sequences of DNA. It looks like they could be engineered in different forms. And, that kind of proposal got funded. And so at that time I started working, and it funded me enough to hire a postdoc to work on it. So I hired a postdoc called Christophe Aguinsky, who's now a professor in France and one of the universities there. And Christophe and I started kind of looking at various DNA structures, and then it was in the year 2001 or 2002 we published our first paper, and then I worked on it for a while until about 2006. And then I moved to Canada. And when I moved to Canada to the University of Waterloo, it was a little bit difficult for me to continue this area of research, because there the funding mechanisms were a lot more applied as a professor of electrical and computer engineering. So that's kind of one of the main reasons I moved back to the US, is I kind of wanted to look at these more far out type of problems rather than near-term problems. And it turned out to be a really good decision, because my since coming back to the US in 2009, I've had a number of proposals that got funded in this area. So it kind of all started out with, I would say a dinner table conversation with my wife, followed by a computer vision engineer at NASA who turned out to have a biology degree, and then and it's kind of a truly remarkable structure, because if you look at nanoscale systems, right? So the challenges in nanoscale systems are, especially from an electronic device viewpoint, because that's what I specialize in, is how do you engineer different materials which have different work functions together, and how do you engineer them in a manner that is reproducible? Okay, which means it's not enough if you make one of them. You have to make them with a very, very high probability. Okay, so that's the second thing: materials with different work functions, building them reproducibly. Okay, and then the third thing is how do you kind of place them at specific locations? Okay, so and so when I say and when I kind of talk about this, I kind of don't mean this as just it's important at the level of a single device. So that's what I was interested more back in 2000. But but single devices are not good. So we should kind of be able to assemble many devices interacting with each other, and then be also able to place them at a specific location. So thinking of it in more conventional terms, you can think of it as, how do you make metal semiconductors and insulators? How do you join metal semiconductors and insulators in very reproducible manner? Okay, and how do you join many devices made out of them together? And how do you place them where you want to on a substrate or in space, so that you can? So these are the important things. And so if you look at DNA, so DNA is kind of quite remarkable, because it has 4 building blocks, okay, and A, T, C, and G. And these 4 building blocks have, distinct work functions. So chemists call them ionization potentials, but we can think of them as work functions. And then a long time back, biochemists had figured out how you can engineer DNA strands with any which sequence together. Okay, so basically you're taking objects having different work functions, and you're learning how to connect them together. And once you learn how to connect them together, you basically have a p-n junction. For example, a p-type material and an n-type material have different work functions. And so if you take a bunch of DNA strands with one work function and other with a different work function and join them, you have in principle, a p-n junction type material. So with DNA, it gives you kind of the possibility to do this. And then with the advance of DNA nanotechnology, around 15, 20 years back, they also found how you can build bigger 2-dimensional and 3-dimensional objects with DNA. So which means that you can potentially assemble many devices together Okay, it solves one more kind of problem. The third problem is, how do you then take this object and place it at a given location so that you can put electrical contacts and make measurements? That remains an unsolved problem, but but at least a lot of advances in the first two areas where joining objects with different work functions, and the second thing is trying to build larger elements where you, by self-assembly, you can build a larger circuit. That is also in principle possible, not done in electronics, but done in other contexts. So I think it's mainly, to me, it's mainly, we need a larger critical mass of scientists working in this field to create that change in fabrication. Right now, it's a few specialists working, so you started off saying the nanoelectronics modeling is a small group, right? If you now take the DNA group, it's even smaller. So we need a larger critical mass of people who think how to kind of assemble this. So right now, I also work with chemists who are somewhat better at thinking about some of these challenges. So in that thing, one thing that DNA has so far lacked is we can control the junction between materials having different work functions. That is possible. So we can build heterostructures, but primarily they are semiconductors, large band gap semiconductors with a band gap that is larger than 3 electron volts. So there are two more things that are necessary for us to think in terms of electronics. One is that for electronics, we need to make connection to conducting objects. Right. We need metallic interconnects, right? And especially for electronics, you can do other things without having metals. So, and the second thing is, it would also be great if one can find ways to control the location of Fermi energy inside the DNA, within the band gap of DNA. And so that in conventional electronics, we'd achieve by doping. So these are two areas that currently we are quite actively working on with our chemist friends. And I will actually talk about some of this in my IEEE Nano tutorial. So a lot of this is happening because chemists also know how to put in metal particles, metal atoms into DNA, how to intercalate them. So kind of bringing in a new species into this self-assembly, a variety of metal atoms into them. So that helps us further engineer the band structure of DNA. And so that is kind of currently the most active component of research in my group. Yeah.
That's fascinating. And so one final question too. So what kind of technologies do you foresee being enabled by this kind of novel DNA-based device?
Okay, so one would be the creation of new materials that don't exist. Okay, so it could be artificially engineered topological materials, which have unique transport properties, where we place atoms in a DNA scaffold, and so that they can realize specific properties. We can also include magnetic atoms into a DNA scaffold. So also applications where spin-spin interaction is important. So bringing in materials where spin-spin interaction between neighboring units plays a role, and ability to kind of artificially engineer it. So these are I would say in the more material science type of framework. Then one can, a more kind of near-term thing in my mind is sensors. So where we are able to kind of sense mutations in DNA, but sense mutations in DNA by passing current through DNA. So we have done a little bit of work on this since about 2018. So basically, if you have a perfect DNA strand without any mutations, and let's say that there's a natural mutation in the human body, and this can be seen in COVID, and we have a couple of papers in the Chem archive on this. So if there is a mutation, so that there is not a perfect match between two complementary base pairs, so A and T basically hydrogen bond. But if it is A and C, the hydrogen bonding between the two of them is not effective. And our calculations show that it also alters the charge transport through them. So this is something that can potentially be detected electrically. So I'd say sensing. So I'd say that overall, like two areas. So one is creating artificially engineered new nanomaterials, okay, such as topological materials and materials where spin-spin interaction plays a role. And on a second front, it would also play a role more in a more conventional sense in terms of building electrical sensors or to detect mutation in DNA, and also electromechanical sensors, because the DNA conductivity is very sensitive to the conformation, which can be changed by applying tiny forces. So you can have an electromechanical switch that comes out from it.
That is absolutely fascinating, and I'm looking forward to hearing even more about this in the tutorial session of IEEE Nano 2024. So thank you, Professor Anantram, and we'll see each other in Gijón.
Okay. Thank you, Luiz. Take care and have a good one. Bye.